This is my first video for spinning numbers, and in honor of that, I'm going to work on the very first video that I did for Khan Academy back in 2016. So here's the circuit that we're going to work on. This is a circuit we received from a student, and she was studying for a physics test and wanted to know how to solve this. In the previous video, I pointed out this is a trick question, and that's the reason it's a trick question. Here's the trick. We did this in the other video. I can connect a wire between here and here, because I know that these two nodes are at the same potential with respect to this node over here. And that simplified the circuit and allowed us to solve it pretty fast. But suppose you don't see this trick. Let's now go and solve this with a conventional circuit analysis method. And to remind us, what we're looking for is this current here. We want to find current I in this wire. So we're going to solve this with the node voltage method. And we're not going to do it with any tricks. We're going to basically apply this method and see what happens and see how it turns out. So let me list out the steps of the node voltage method. First is assign ground. And that's the same thing as saying assign a reference node. Second thing is to give node names, assign node names. Step 3 of the node voltage method is to solve any easy nodes. Step 4, I'll tell you what an easy one is in a minute. Step 4 is to write Kirchhoff's voltage law for the nodes, KVL, Kirchhoff's voltage law at the nodes. And step 5 is solve. Step 4 is going to produce some equations for us. Step 5, we solve those equations. Step 5 solves us for voltages. Step 6, we solve for the currents. All right, let's go for it. Okay, step 1, assign a reference node. I'm going to pick this node here and make that my reference node. And that's the symbol for a reference node. And the reason I pick this node is because I look for the voltage sources and I find out which node the voltage sources are connected to. So these guys are both connected to this node. This seems like a good place to do it. You could choose other places here. You could choose this, you could choose any other node in this circuit. You could choose this one here if you wanted to, but that means that there's no voltage sources connected to this one. So this guy over here in the corner is definitely a good candidate. Okay, that's all it takes. So let's now give names to the other nodes in this circuit. All right, there's node here. We're going to call that node 1. And there's one here. We'll call that node 2. And there's one big distributed node here, and we'll call that node 3. And each of those nodes has a voltage, a node voltage. Now, while I'm at it giving things names, let's name the resistors just so it's easy. We'll call this R1. We'll call this one R2. We'll call this R3. And let me give some names to some currents as well. That we'll call I1. We'll put an arrow there. We'll call that I2. And for I down here, let's call this I3. So I pointed these arrows. I just was consistent with the way I pointed these arrows. I pointed them all to the right. It doesn't matter at this point. It's not critical that you point the arrows in what you think might be the right direction that would give you a positive sign on the current. That doesn't matter at this point. You just want to get names and directions on these. And the arithmetic will take care of the signs of the currents and give us the right answer in the end. Okay, so now we've done the node names. Okay, step 3 is solve for the easy nodes. An easy node in the node voltage method, an easy node is a node that you have a voltage source connected directly to the reference. In this case, we have two of those. We have two easy nodes. Number 1 and number 2 are easy. And the reason is that this one's connected to a battery to number 2, and this one's connected from the reference through this battery to number 1. So right off the bat, we can say we know V1. This is an easy node. V1 equals 11 volts. Actually, minus 11 volts. This point here is 11 volts below the reference node. So immediately we know it's at minus 11 volts. And the same is for V2. V2 equals minus 11 volts. Those are the easy nodes. What about V3? Is V3 an easy node? No, it's not. It's not connected to any voltage sources. So there's nothing easy about that one. We're going to have to do some work. So now we've done step 3. Step 4, write Kirchhoff's voltage law at the nodes. And the only node that's left is 3. Did I say Kirchhoff's voltage law? No, that's wrong. Let me fix this. This is bad. Kirchhoff's current law, KCL. We write KCL at the nodes when we're doing the node voltage method. A little confusing. That's okay. Whew. Okay. Step 4, write Kirchhoff's current law at the nodes. And the only node we have left is node 3. So let's write KCL at this node here. And that says, KCL says the sum of the currents flowing into this node is equal to 0. And now I have all my current arrows flowing into node 3. So I can write I1 plus I2 plus I3 equals 0. That's the KCL at that node. Okay, now we have our KCL equation set up, and we're going to stop the video here, and we'll take up what we do with this in the next video.